Alright, so today we're doing Keeper 3.2 least squares regression. Alright, so your regression line is just simply a line that describes your response variable and your explanatory variable. So basically it's like your best fit line. It's the same line that we used to use back in the day in middle school when we were trying to calculate like the best fit line for our equation. The only difference here is that our regression line typically is very specific in that it gives you one of the better lines for the model, for the data. Alright, so our formula for our regression line generally takes the form of y hat equals a plus bx. Y hat is your predicted value, a is your y-intercept, and b is your slope. So this should kind of look familiar. We talked about it a little bit in class, but this should look a little bit familiar. It should look like y equals mx plus b. It's just rewritten with a's, b's, and y hats. Alright, so we have something that we call extrapolation. Extrapolation is basically, it comes into play when you have a line of best fit, you have some data and you get your line of best fit and you're trying to make predictions based off of that line of best fit. But if you try to make a prediction that's way outside of the values that you already had in your data set, that's extrapolation. So for instance, if we were looking at the age of students at Alatuna and their GPA, and we were trying to find like a correlation between age and GPA. Well, as long as your age range fell between like, I don't know, 13 to I guess 18, well then the data should give you a good prediction. But if we ask, like say for instance we had some kid that's been here forever and he's like 22 years old or something crazy like that, and we wanted to figure out his GPA based off his age of 22, well, that's extrapolation because the data probably is not going to give us a valid solution. His GPA is probably going to be somewhere like really, really high or really, really low depending on the depending on the data itself. But if we don't want to use any number that's super far outside of the data set. Alright, so oftentimes we want to find residuals of our data set. A residual is basically the difference between the observed value versus the actual predicted value. So it's the difference between what we actually see versus what we predicted. Now again, remember our line of best fit. So in this example down here, let me get my highlighter. Here's my line of best fit, right? Here's my regression line. Alright, so this regression line does not necessarily touch every single point in my data set. However, it's going in between those points. So basically what our residual is the distance from the point, from the actual data value to our predicted line. So this was our observed and this is our predicted line, and we're looking at that perpendicular distance to figure out our residual. The easiest way to do it is simply take your observed y and subtract it from your predicted y. Alright, keep in mind that negative residuals are below the line, so we'll get negative values when we calculate the residual, and positive residuals are above the line. Alright, so your least squared regression line, which is what this keeper is really all about, is the best fit line that's truly the best fit. You guys know if I ask you to sketch out a best fit line and I ask somebody else to sketch out a best fit line and this person sketch out a best fit line, we could all get different best fit lines. Well, the least square regression line is truly the best one for the data set. So what it basically does is it makes the sum, so all of these little things is the sum of the squared residuals. So all these little squares, it makes it so that that's very, very small. In other words, I'm trying to find a line that reduces the amount of residuals that we have in the data set. Alright, I don't want a lot of stuff. I just want to reduce it. So this line that we have right here, if this is your least squared regression line, this is actually the best possible line for the data. Alright, so we can actually find our residual, or I'm sorry, our least squares regression line. We can actually find that on the calculator if you have your data set. Alright, so if you have your data set, you know you go to stat, edit, and you put the data in. But oftentimes you don't have the data set, and all you have is like some values or some stuff they already gave you. Or if they gave you some statistics without the data set, you can still figure out your least squared regression line using this formula. So basically, we can still figure out the slope as long as we have our correlation coefficient, which is our R, and our standard deviations of both of our variables. So basically the slope is R times the standard deviation of our Y variable or our response variable over the standard deviation of our explanatory variable. And then if we want to find the y-intercept, we have A equals, this is the mean of the y variable minus the slope that we just found above times the mean of the x variable. Now you got to remember your least square regression line. For any least square regression, if it's truly a least square regression line, the mean will always pass through that line. Alright, the mean of your data set will always pass through that line. So that's why we're able to use our mean to find our y-intercept. Alright, with that being said, again, we want to always try to, graph our data, figure out what we see, notice any trends, any patterns. We also always look for outliers and any departures from those patterns. Well, a residual plot helps you to see if you have any departures from your pattern. If you have anything that looks fishy or anything that looks funky. So a residual plot is very, very helpful in trying to figure out how well the regression line actually fits the data. Alright, so here's our regression line. And from that regression line, I can actually make a residual plot showing all of these little distances from the observed to the actual predicted. Alright, so that's showing me all the little points. Alright, so what you want to be really careful of, and I'm going to actually write this down because I think it's good, and I think you need to make sure you get this in your keeper. But if you see a pattern, y'all don't laugh at my writing. So pattern, if you see a pattern in the residual plot, that equals problem. Pattern equals problem. Alright, so again, if you see a pattern in your residual plot, you know that you have a problem with the original data. So in other words, a pattern tells me, and it's right here, a pattern tells me that the linear model was not appropriate. I shouldn't see a pattern. Alright, I should see something more like a random scatter about this line in the middle, this line y equals 0. Alright, so for instance, on this problem, I see this curved pattern, this is a quadratic, reflected quadratic. This lets me know that this line of best fit that I tried to use in the original data set, it wasn't very good. I probably should have, instead of doing a line of best fit, I probably should have found a quadratic equation or something like that. Alright, so we can actually figure out the standard deviation of our residuals. The formula for your standard deviation is given right here. Now remember, what does that mean? Standard deviation is the average value that your values will be, or the average amount that your values will be from the mean. So I'm looking at the average residual, and I'm saying how far my data values differ from that residual. Alright, so we also have something called the coefficient of determination, which is R². Now remember, R is a coefficient of is a correlation coefficient, and R² is your coefficient of determination. So your R² value basically tells you how much of your data is explained by the model. In other words, did the equation that I find really do a good job in explaining or in predicting what we needed to predict. So ideally you want a really high R² value. You want a number that's very close to 1, because you want your model, you want your regression line to be very good at predicting values based off of your data set. Now remember, your R² value can never be negative because it is squared. So we're literally taking our R value and we're squaring it. A lot of people get confused about that. If I give you R, you should be able to find R². If I give you R², you should be able to find R, because you could just take the square root of it. So here's your formula for your R². But generally, we don't really calculate it by hand. This is just saying you can calculate it by hand, but generally we don't. We just use the calculator to figure out our answers. But if you did want to calculate it, SSE is if you sum up all your residual squareds, and then SST is if you take your y values minus the mean of the y values squared and sum all those things up. Alright, so another important thing that you guys need to make sure you're able to do is actually read computer output. So a lot of times, like in statistics, statisticians won't calculate stuff by hand. They'll plug it into some software and they'll get an answer. But the computer output basically tells you everything you need to know. And although you guys don't have the software yourself, you still need to know how to read the software. So when I'm looking at this is software from Minitab, which is a very popular statistical software. Some other popular ones is like Jump. You have SAS. There's a bunch of them, but Minitab is the one that I prefer and I use more often, and that's the one that you see a lot on the AP exam too. It's very, very, very user friendly, and it basically spells out everything you need to know. So in this computer output, this top number, the one that's right next to constant, that's your y-intercept. That will always be your y-intercept. Alright, whatever your variable is, in this case our variable was NEA change. This can be whatever, that's per problem. It changes per problem. It could be fat, it could be backpack weight, or whatever. Whatever the variable is, this number is telling you the slope for that variable. Alright, this is your standard deviation of your residuals, and this is your R-squared value. Alright, and we can use this R-squared value, take the square root of it, and we can get our R value. Don't worry about this adjusted R-squared value. That's like if you had multiple regression, like if you had multiple y variables or multiple x variables, something like that, you would use adjusted R-squared, but we don't do that in this class. And these other ones over here, like your T and your P, your standard error of your coefficient, we do this later on in chapter 12 of this class. Alright, so here's your jump output. Again, you don't see this very often. Most of the time you see Minitab, but it's the same kind of situation. Your intercept is telling you that's your y-intercept. Here's your variable, so the number next to variable is your slope. And then you also, again, you have your R-squared, and you have your standard deviation of your residuals. Alright, so remember, a couple things you really want to make sure you understand. Correlation and regression lines describe only linear relationships. If you have some other type of relationship like exponential or quadratic or anything like that, you wouldn't use a regression line or correlation. Correlation and least squares regression lines are not resistant, and basically that means if I have a crazy point like an outlier or influential point, if I have anything like that, my line is going to be swayed by that point, and my correlation is going to be swayed by that point. So they're not resistant. Those outliers do affect. Remember, the only thing that we've really talked about so far that was resistant was your median and your interquartile range. Everything else, like the mean, that's not resistant, just like the correlation is not resistant, and the least squared regression line is not resistant. And here you see it right here with these points out here. So with this green line is just your whole data set, and then this red line is if I was to remove this point. You see the line change. And this blue line right here is if I move this point, and again it changed. So you see, as I add and subtract points, my data, my line, my least square regression line is changing. And you see what's really changing here is the slope of that line. Alright, so correlation, no, it's not what I want to say. Alright, so basically, again, we already know we have outliers. Outliers, when we discuss our outliers, we'll say they're potential outliers. We won't technically calculate whether or not they're outliers or not. A lot of times those outliers will have really, really high residual values, but not always. And then you normally notice it's an outlier because the y value is way different than the y's of the other values or the other data values in the set. An influential point is a point that if you remove it, if you take that point away, your calculations, like your least square regression line, your correlation, all those values change drastically. All right, so those are influential points. Usually these points are like outliers in terms of their y is really far off and their x is really far off. Like this point is just like really out of control, way outside the data set. It's like if everyone failed the test and everyone got no sleep last night, and then one person got a bunch of sleep and then did really well on the test. That point was really far away, so that would be considered an influential point. Alright, and the last thing we want to make sure we understand is that association does not imply causation. So just because we see a relationship, like we see a positive trend or a negative trend between two variables, that does not necessarily mean that one variable caused, or one variable caused the other variable. Alright, so it could be just that there was some relationship. So like if I look at this example, it says a serious study once found that people with 2 cars live longer than people with only 1 car. Owning 3 cars is even better, and so on. There's a substantial positive correlation between number of cars X and length of life Y. So the thing here is we see a relationship. We know there's some type of association there. I see that people that live longer have more cars. But is that to say that because you live longer or because you have more cars, you're definitely going to live longer? Is it saying that the fact that you had more cars, is that saying that that's what's causing you to live longer? It's not saying that. Basically, all it's saying is that there's a relationship here, which makes sense because if you probably live longer, you probably had the need to have more cars because, maybe your cars went bad faster or whatever the case is. But it's not saying that the fact that you had more cars caused you to live longer. Alright, so you don't want to mix that up. You don't want to assume that just because there's a relationship, one caused the other. Alright, that's it.